Okay, so hopefully with the last series of lectures, I've gotten you really excited about all of these different structural and stratigraphic features that we can see in Seismic, right? And so now I'm going to go more into how we apply methods of seismic geomorphology in interpreting our 3D data. And so one of the critical aspects of this is iterating between plan and section views. So the vertical section and time or horizons. And I'm going to cover a lot of different ways that we can kind of visualize the data and move through the data and think about it to improve our geologic interpretations. All right, so first off, know your analogs. I've said this a million times. So some of the examples that I'm going to be showing in this kind of mini lecture have to do with deep water, kind of moving off the shelf geomorphology. So it's always great to ground yourself, pull out an old textbook to become familiar with what types of features might I see. So as we come off the shelf, we'll have perhaps more of like a canyon bypass channel system. We may get into a slope valley system, as I'm showing over here. It may be weakly confined depending on, if the gradient changes, or when we get to the basin floor and we have a very low gradient, we may see some of those distributary lobe systems, those fans, those lovely sheet sands that are great reservoirs. So know your analogs first off. And then once you kind of have an idea of what you're working with, you can go in and you can go between the plan and the section view. And so this is an example from one of Postman-Tier's papers where he's got his analog and he's showing it in time over here in the upper left, where we see this lovely frontal splay down on the basin floor. We've also got some examples in this system of a backfilled canyon in Seismic. So right kind of here as we're coming off the slope of the shelf. Over here in B, so kind of off to the side here, we've got some levees and overbanks, a turbidity flow levee channel. And then down here in more of that distributary, like on the basin floor, we can see a lot of different debris flows that are stacked up on top of one another. So all of this is kind of wrapped into that seismic geomorphology. When we look at seismic, like in this case, we're looking at a bunch of time slices. I would have trouble just looking at these and knowing, okay, which of these are from fluvial systems or which of them are from deep water systems. It's very hard to tell just looking at the horizon or time slices. And so that's why we want to go back and look at the vertical sections at the same time and incorporate both views into our interpretation. And so in this case, we've got more of a turbidite system. From A to A prime, we can see a lot of these turbidites and mass transport deposits that are kind of stacked up on top of each other. This is a deep water environment. Here we're looking at some fluvial features. So you kind of see these lovely scroll bars in the time section. But when we look at it in vertical section, this is a very, very subtle feature. So hard to see in this case. And I see a lot of these in the kind of shelf of the Gulf of Mexico, where I would have no idea that there's a channel there until I alternate over to the time slice or horizon slices to actually realize that there are some channels. Here's some examples of point bars and what they look like. And so you could see a nice visualization of the seismic and then a cartoon explaining it. In this case, we can really get an idea of where this channel ended up because it's kind of the last iteration, the final channel position. And even when we look at it in the cross section here, there's a little bit of evidence of some patterns of how that point bar accreted, so the lateral accretion from it. Here's a deep water levee channel, not the highest resolution, but you can see we're pretty zoomed in. So this yellow bar is just 100 milliseconds. And when we look at it in the vertical section and then the time slice, in the vertical section, we see a lot of these little disruptions that over time knowing your system, you'd be able to recognize as potential channels. And so it's kind of like, okay, well, are we looking at 5 or 6 different channels here? Are they all parallel to each other, but really it's a highly meandering system. And that's something that we could only notice if we also look at it in time, like a time section. So it's very, very sinuous, and we've crossed over the same channel many times. So there's a lot of visualization kind of tricks that you can use to understand what's going on geologically. And I'm going to go through these. So these are features like slicing, stacking, datuming, illumination, flattening. Even there's a technique called double flattening. And so as we've kind of talked about, there's a lot of different ways to slice your 3D data. So you can have your horizontal planar slice, so a time slice. You can also have a horizon slice. And you'll notice between these two that they actually look fairly different to each other. In the horizon slice, there's probably a slight dip to the system. And so when we map the horizon, we could actually see the channel over on this left side a little bit more clearly. And then how it looks like it splays out on a basin floor. As I mentioned in a previous lecture, you can also do an inclined planar slice, so a dipping time slice, if you want to try to just quickly image the channel without spending the time to do the full horizon mapping. And so here's an example of what those may look like. So in the time slice, you could see we're cross-cutting and only seeing that yellow interval of interest of that channel system for a little while. While as with the horizon parallel slicing, if we're able to mimic, if there's a fairly steady dip, we can kind of mimic a horizon slice and see more of the channel, or horizon parallel slice. And so here's a nice animation that kind of goes through it. So we've got our seismic volume. Here we've got a time slice. And so that channel only appears on a portion of our time slice. A dipping planar slice, if we're able to do it very parallel to the reflections, we're able to see the channel more in full. A horizon slice, is probably a little bit more accurate depending on the variation of the dip. And you'd be able to see the entire channel. And then you could also do that optical stack method that I've talked about, where you kind of take a thickness of the seismic cube, so maybe 50 milliseconds or so, and you render part of it transparent in your software. And then that would let you kind of see the full channel as it wouldn't be transparent. And so here's an example of optical stacking to enhance visualization. So in this case, they took 80 milliseconds of data, so right between these two dotted lines, so kind of zooming in here, and you could see these channels that appear as the bright reflectors, and they optically stacked it. So up here in A, we've got the optical stack, so you can see all these intertwined fluvial channels in the system, as compared to B right here, where we've got, hold on, I'm trying to quickly read through my notes, just the time slice. So in both of them, we could tell there's a lot going on, but we get a better sense of the channel, fluvial channel system when we've done that optical stack. Here's another case where we could change our slicing technique for a braided fluvial channel system, shown as an example. And this is using some more creative datuming, where you're kind of picking the datum that you want to use that best matches with what you're trying to reveal in the seismic data. And so there's a lot of different ways to change your slicing strategy in order to work your way through the system. So here's an example. And this post-Mentir 2022 paper is really key, as I mentioned before, for seismic geomorphology. This paper that I'm grabbing figures from, they've taken a lot of information over decades of study and kind of put it into a very long but very, very thorough paper that talks about the methods of seismic geomorphology. So anyway, in this case, we've got our time slice. And so we could see portions of, it looks like a channel system. Now we've got a dipping arbitrary planar slice. And then down here in D, we've got our more creatively datum slice. So you're able to image more the channel system itself. And then here we've got a multi-horizon flattening slice. So let me go through some of that more. So with creative datuming, what you're doing is you're trying to pick a datum. So it's not quite flattening, it's not quite dipping, it's not quite a horizon slice. But you're trying to pick a relative way to pick the horizon to image your channels. So channels don't always occur just on one horizon, like a lithologic bed would. And so you could do this by just creating a grid, like a coarse grid in your seismic data, and then interpolating. So it's easier to do than it sounds. And so here's a case with creative datuming, looking at a submarine canyon system. And then, here we're looking at it on that creative datum that they've picked about 12 milliseconds above the base of the canyon. And then here's an optical stack where they've taken 20 relatively close together slices and optically stacked them together. And so now you could see all the different evolutions of this submarine canyon system as it goes out and splays more on the basin floor. So really beautiful stuff. I will pause to say here that some of the work by Henry Postmentier is why I became a seismic reflection geologist, is because looking at images like this, it almost feels like I'm looking out of an airplane window and not at something that's buried miles deep in the earth. Other ways to get more information from your seismic data is by changing the perspective. So a lot of the software packages that we have access to, or that you may have access to, you can rotate the directions, you could zoom in. And so here's another deep water example from the Gulf of Mexico, using some lighting techniques, illumination techniques. You can see how there's mounding on parts of the deep water channel, particularly when you zoom in. You could see the mounding of the levees. You can see the kind of rippling of the sediment waves over here. You can also see internally, in this case, how the channel looks mounded. And then as we move down the channel, it suddenly looks more sunken or concave. And that's because we have a change or it's likely because we have a change in the lithology of the channel fill. So going from more sandy facies, which would appear more mounded and seismic, to a more mud-rich system as we get further away from the source. Here's an example with carbonates where we're kind of changing our perspective. So we can see this really lovely example offshore Indonesia, where we've got these tidal channels working their way through carbonates. But if we zoom in, we can suddenly notice, and we play with the lighting a little bit, we can suddenly notice all these small little patch reefs, which may be of interest to us. So these patch reefs are about 100 meters or so in diameter. I mentioned illumination. So this is a great tool to use, particularly once you've mapped out a surface like a horizon, because you can change the direction that your light source is coming from. So in this case, we've got some ridges, and you can see the difference between shining the light source parallel to the ridges, as we're showing on the left, to perpendicular to the ridges, as we're seeing on the right. And so these are beach ridge deposits that changing the light source really allows us to kind of amplify the subtle structure of them. Here's another example in a different system where we are looking at the light source from 4 different directions, like ordinal directions. And you'll notice that we kind of image different patterns, I think these were like different fractured areas that we're able to see as we change that light source. And so this is something, we always end up with these static images that we use in PowerPoints or papers or research reports. But there's a lot to be said about making movies of what you're seeing in your seismic workstation. So you can imagine interactively changing your light source and your illumination and really revealing how there are these subtle kind of elevation differences in your horizon. So movies are becoming more and more common as ways to communicate what you're seeing, because we can see different patterns as we move through the data, as we scroll through the data, than we can in just one flat image. Here's another case of illumination where if we look on the left, it looks like we have very nondescript. We see a slump scar, we see some canyons. Obviously, we're quite zoomed out. We can see some hints of pockmarks. I think some of this is also a case of not having an optimal color bar because all the green kind of blends together. But even just using illumination, we're adding in these shadows on the right-hand side that reveal so much more structure. So you see a lot more details of the slump scar. You could see more slump scars up here, closer to the shelf. You can see the wide proliferation of the pockmarks and just a lot more details of the canyon systems. Straddle slicing is another method. In this case, I've mentioned this before, where you can pick 1 or 2 horizons and then do straddle slices like 10 milliseconds above it, 20, 30, 40 milliseconds above it, as kind of shown here. You can also pick 2 horizons and then do proportional slicing between them too. So that's proportional slicing. And so this allows you, particularly in this case where you have a lot of, you don't have a lot of difference, time difference or thickness difference, time thickness difference between your horizons. You can map 1 horizon in detail and then use the straddle slicing technique as a proxy to mapping out 10 or 15 different horizons. You can also use this more kind of proportional slicing method that I just mentioned. In this case, and it's a great example in the paper, you may have that kind of funny looking thing, that FLT that you're trying to understand in your seismic data. And you've got a few reference horizons that you can map out. You could try shifting it down relative to the top horizon and kind of seeing part of it. You could try shifting it up relative to the bottom horizon, but since you've got this time thickness, it's still not quite right. And so in this case, you can do that proportional slicing to get right in the middle and really try to image a horizon that really reflects the location of that funny looking thing. You can also do a technique called double flattening. And so in this case, let's see if I've got this marked well. We've got a reflection A up here on the top. If you could see follow my cursor. A reflection B down here on the bottom. And then we've got these kind of carbonate reefs in the middle. And so if we flatten on the top horizon, okay, so we're flattening on reflection A. So we've done a single flattening. We've still got a lot of pull-up down below it because of that velocity difference. But what we can do instead is we can double flatten. So we can flatten on both the reflection A and the reflection B. And so that can help us kind of mitigate or eliminate as much as possible some of the differential compaction issues, as well as the velocity related pull-up effects. And so here's another case that I'm just going to kind of go through really quickly, where we've got some features that we're interested in seismic. So notice that you really have to zoom in. We've got a lot of noise here, very small scale features. So we've got our original horizon that we've mapped and maybe let our horizon kind of track to, so it's a little bit jittery. And then we've created our smooth horizon, which better represents it. We can flatten it. Okay, so now we've flattened on that lower horizon, and we see some interesting noise trains in this example. And those become a little bit more prevalent after we've flattened. So things we want to be aware of. And then in this case, we've got another case where we could use flattening, where we have a differential compaction kind of bump in this area. So we've got a channel complex. It looks like we've got some mounded sands. It looks like there's a little bit of a reflection pull-up that we're worried about. And so we've got this upper datum that we've picked, and then a lower datum. And so we could flatten on the lower datum right here. And that helps minimize the effects of the velocity contrast below it. Or we could flatten on the upper horizon, or the upper datum right here. And so that kind of gets rid of the differential compaction from the channel, but we still have those velocity related kind of sags. And so we do a double flattening on the upper and the lower, and that gets rid of the velocity issues and the differential compaction issues. And so just kind of some key concepts to wrap up here. Of course, we want to view in 3D. We want to look at the time slice horizon slice, map view, as well as the vertical view. So the inline, cross line, arbitrary line. You really, in this case, when you're doing seismic geomorphology, you really want to know and do some research and have a good understanding of your analog system, so that you know the different aspects that you may be looking for, that you may want to search for in the seismic data. And then there's a lot of different visualization techniques to try. So I mentioned the slicing, the stacking, the datuming, the illumination, flattening, and double flattening. So in any case, thanks for listening again.